Hi class. Today our topic is density. We'll start off with a few fun demos and then we'll get into the chemistry behind what you're seeing. Hope you'll like these demos. They're a little bit, shall we say, counterintuitive. The first thing I'm going to do is show you a demo about pop cans. So I want you to predict, I've got some regular pop cans and some diet pop cans, and I'm going to put them in a tank full of water. And what I want you to do is just take a moment, pause the video, take a moment and see and make a guess. What do you think is going to happen when I put these cans into the water? Will they sink or will they float? And does it make a difference whether they're diet or not diet? Does it make a difference whether the type of pop it is? So take a moment, just write down your predictions, and then let's see how they turn out. All right, guys, so let's do our density demo with our pop cans here. So I'm going to take let's take a few diet cans. Here I have a Diet Mountain Dew. You can see it's a 12-ounce can, regular 12-ounce can. I'm going to drop my Diet Mountain Dew into my tank here. And you're going to see that that Diet Mountain Dew floats. Let's try another Diet Pop. Here we have Diet Ginger Ale, Diet Canada Dry. We're going to drop it in here. And what do we see as well? It's floating. Now here I have a Diet Coke. This one has a different volume. This one is 7.5 fluid ounces. So it's got a different volume. Now you notice it's smaller. But I'm still getting, it's still a diet can. I'm going to drop it in. This one floats as well. All right. Here I have some Diet Seltzer water. All right. Let's see what this one's going to do when I drop it in. It floats. Let's try some regular soda now. Here's a regular Sunkist. I'm going to drop my regular Sunkist in there. Wow, look at that. It sunk right to the bottom. It's staying at the bottom. Well, maybe that's just a Sunkist thing. Let's try some Coke. And I've got a 12-ounce can of Coke. We're going to drop it in. What does it do? Look at that. It's sitting on the bottom too. It sank. Oh, come on. Maybe that's weird. Let's try a diet. Let's try regular Mountain Dew. I'm going to drop the regular Mountain Dew in here. And what do we see? We see it sinks right away too. Well, hopefully you found that a bit interesting. I know the first time I did this demo, it was a little bit surprising to me. But what we're really looking at here is density. Density. Now we're going to define density. We'll use a capital D for it. And we're going to say it's equal to little m over big V. The little m is mass, and the little v is volume. Now I want you to think of mass as we're used to thinking about that, or heard that term before. I think about mass as being the amount of matter or the amount of stuff that you have. And think about volume as being the amount of space that you have that mass in. And that will lead you to understanding what density is. So I'm going to do another demo here. And this time, again, I want you to predict what's going to happen when I drop the pop cans into the water. Take a moment, pause the video, and then come back. We'll do the demo and see what you think. All right, guys, so now let's try this again. I'm going to use the same soda cans. We're going to put it into a different container over here. And again, let's start off with our diets. Here's our Diet Coke. We're going to drop it in. We see that one floats real easy. Let's try our Diet Ginger Ale. Point that the right way. Our Diet Ginger Ale. I'm going to drop it in. And you can see it floats. Let's try our Diet Seltzer water. Again, we're going to drop it in. And we're going to see it floats. And finally, last but not least, let's try our Diet Mountain Dew. We're going to drop it and it floats. So that's the same as it was last time. Let's try a couple other ones here. Okay. We just put the Diet Mountain Dew in. Let's try the regular Mountain Dew. Whoa! It floats. Maybe there's something wrong here. Let's try a regular Coke. Let's drop it in. Whoa, it floats too. One more try here. Regular Sunkist. That floats too. Wait a minute. They all float. How can that be? So I want to talk a little bit more about diet pop versus regular pop. Diet pop versus regular pop. Right? We know that water has about 1 gram of mass for every milliliter of volume. So we call that 1 gram per milliliter. Actually, this is a number I want you to memorize. We'll use this throughout the year. And there's only like 5 numbers I think I'm going to ask you to memorize, but this is a very important one. So please memorize this, the density of water, 1 gram per milliliter. Now, if we look at the density of salt water, this was the water that was in my second tank. Density of salt water is 1.18 grams per milliliter. So it's got a little bit more stuff in that volume, a little bit more mass in that same unit of volume. Now we notice that the diet cans floated in the regular water. Right? So if I tell you the density of 0.98 grams per milliliter for our diet pop, hopefully that would make sense to you. It has less mass in that same volume. If it has less mass in the same volume, it's going to float. I mean, we're used to putting things in water that float and things that water that sink, right? Diet pop, it's less dense, there's less mass in that volume, it's going to float. Regular pop, on the other hand, we saw that it sunk in the regular water tank and it floated in the saltwater tank. So hopefully you're going to come to the guess that the regular pop has a density between that of water and between that of salt water. And indeed it does. We're going to see the regular pop has a density of 1.10 grams per milliliter. Now you might ask, how can we do that? They had the same volume. They had the same volume. They're both 12-ounce cans. What the difference is, in regular pop, they sweeten it with sugar. They sweeten it with sugar. Look how much sugar there is here. That's a lot of sugar that goes into the can of pop, right? How about the diet pop? It uses an artificial sweetener, and they don't need to use very much at all. So look at that. Look at the difference between these two. A lot of sugar and hardly any of the NutraSweet or saccharin. I can't remember which one this is. When these dissolve, they fill in that spaces between the water molecules, so they don't increase the volume. But think about it, this has a lot more mass that's now stuck in that volume compared to this little bit here from the artificial sweetener. And there you go. That's why you can explain that diet pop will float. Same volume, but the mass is very different. Now we'll move on to our second demo. We're going to talk about some graduated cylinders. And we're going to put some golf balls in those. And again, you're going to see something a little surprising. Hello, class. Now it's time for our next demo. So I've got 3 golf balls here. They're all kind of pinkish golf balls. Hold them up so you can see them. Right, and I've got 3 graduated cylinders. So we're going to take what we learned a little bit about density here, and I'm going to show you another weird thing here with density. So I'm going to take this first golf ball, right? They're all the same golf balls, and I'm going to drop it into the water here. And we're going to watch that golf ball. It's going down, 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 down. Awesome. So what does that tell you about our golf ball? Is it more dense or less dense than the water? Well, if it sinks to the bottom, right? If it sinks to the bottom, that means it's more dense, right? The more dense things go to the bottom, the less dense things stay on the top. So I'm going to drop it in our next tube. Say different golf ball. Well, different golf ball, and wow, I dropped that golf ball in. Look at that. It just sits there on the top. So what's that telling you here? Well, hopefully you're thinking, I must have different things in these 2 graduated cylinders because the golf balls didn't change. And you'd be right? This graduated cylinder here just has regular water, and we saw a little bit ago regular water has a density of about 1 gram per milliliter, right? This one, I'm going to tell you, has salt water in it. And we saw a little bit earlier, too, that salt water has a density of 1.18 grams per milliliter. So that our golf ball is floating here, that tells us what? It tells us it has a density that's less than the salt water. That's why it floats on the top. So we know that the golf ball's density must be between 1, right? Because this is the one where it sank. This is 1, and it sank to the bottom. And it must be less than the 1.18 of salt water. All right, makes enough sense. Let's drop our golf ball in the third graduated cylinder. And let's see what happens here. Sinking down, sinking down. Whoa, look at this one. It stopped halfway down. How could that happen? How could we have it sitting halfway down? I'm trying to be a little fun here. What I've done with this graduated cylinder is there's some salt water in the bottom, right? And we know that our golf ball will float on top of salt water. So here it is. It's floating on top of the salt water. And then I poured some regular water in the top, and I was really careful how I did that so it would not mix. So up here we have regular water. And we know from over here that our golf ball is going to sink to the bottom of the regular water. And that's exactly what it did here. It sank to the bottom of the regular water, but it stays on top of the salt water. So you can have some fun with your friends, amaze them with your knowledge of chemistry and your magic skills. You can show them how you can get a golf ball to float halfway down. So how do we explain what happened here? Well, the first cylinder was full of just water. Right? We put the golf ball in there and it sunk right to the bottom. So what does that tell you? That tells you that the golf ball must be more dense, right? We know the more dense things are, they'll sink to the bottom. Whatever is the most dense sinks to the bottom. The less dense floats on top. So in the second graduated cylinder I showed you, this was just full of salt water. And we saw that the golf ball floated on top of that salt water. So how do we explain what that third one was? The third one, it had salt water in the bottom and had regular water in the top. So when we drop the golf ball in, we know it's denser than the regular water. So it sank down to the bottom of that regular water. But I poured that regular water in really carefully so that it was just floating on top of the salt water. So when the golf ball hit that middle part where there was salt water below and water above, right, what happened to the golf ball? It floated, right? It sank to the bottom of the water part, but it floated on top of the salt water part. Now we're going to do a demo about soap, and this one's also fun. Hi, class. Now for our last demo on density. I've got a little piece of ivory soap here. I just cut a chunk of ivory soap off. And I want you to guess, what's going to happen when I put this ivory soap in the water? Take a second. Write down what you think is going to happen. All right, let's drop it in. Hopefully you can see it floats. Now, why does it float? Well, if we know if something's floating because it has less density, right? The thing that floats on the top has less density than the thing that it's floating in, right? So we know that this must be less dense than water. Well, does that make a lot of sense? I mean, I can pinch this soap, but it doesn't pinch like a balloon. This is solid. Why is it floating? Well, what if I told you there's a lot of air bubbles inside of this piece of soap? A lot of air bubbles. You'd say, well, Dr. Yates, you can't squish it like a balloon. What do you mean there's air bubbles? I said, well, there is. And how can I show you that there are air bubbles in here? I'm going to take this piece of soap and I'm going to stick it in a microwave. Now, what happens to air when you heat it up? Right? It expands. Hopefully you know that. We'll learn a little bit more about that closer to the end of the year. But it expands. So I'm going to take this, put it in the microwave, and let's watch what happens. I'm hoping you can see that soap going in the microwave. Look at what's going on there. See, the soap is expanding. It's blowing up. Oh my gosh, look at that. Let me take it out real quick and show you what this looks like. There you go. Our soap has literally expanded. It's blown way up. I don't know if you can see that. This thing is huge now. Really big. All right, so what do we see here? With that air expanded the bubbles in here and it blew our soap up. When we heated up that air bubbles inside of the soap, that air bubbles expanded. It caused our soap to expand too. And we had this funky, creamy stuff. Pretty cool. So that's another way we can think about density. You may have seen a map like this before. This is a map of the United States. In the darker areas here, if I can get my mouse to show up, there's more people. Right? In the lighter areas, there's less people. So I hope you know, right? California's got a lot of people. Florida's got a lot of people. The Northeast has a lot of people. But the central part of our country, the plains and the mountain states, there's not a lot of people. And so you see that it's not as dark there. And we give another example here of these two cubes on the right. Right? You see, I've got a bunch of dots here representing molecules. The one here that's in blue on the left, there's hardly any molecules. It's less dense. The one here on the right, there's a lot more molecules. Both boxes have the same volume. The one on the right has more molecules, more stuff, so it's going to have a higher density. Now, density is a physical property. We call this a physical property, and we'll learn a little bit more about that in a week or so. But we also call this an intensive physical property, or intensive property, because it does not change with the size. It doesn't change with the amount of stuff you have. Right? We know the density of water is 1 gram per milliliter. Right? Because it's intensive, we know the density of a particular substance is always the same. So if I went out and looked at the density of Hoover Reservoir, we got all that water out there, a lot of water, it's going to have a density of 1 gram per milliliter. If I took a little cup of water, right, like you would have at your home, and filled it up with water, it would have the same density, 1 gram per milliliter. Again, it doesn't matter how much we have, right? Whether we have a cup or we have a whole reservoir, the density doesn't change. It doesn't depend on how much stuff you have. That's why we call it an intensive property. Again, once more, the equation for density is D equals M over V. Density for the big D, M little m for mass, and big V for volume. Now I'm going to show you a trick that helps you use this equation when we get into calculations. We call this our triangle trick. I'm going to draw a line partway through the triangle, about halfway down. I'm going to draw another line in the bottom. So I'm going to split the bottom into 2 parts, a left and a right. Maybe you've seen this in your math class before, but if you haven't, we're going to go through it and explain it. So on the top of this triangle, I want to put a little m. A little m for mass. The bottom, we're going to put a big D for density and a big V for volume. So how do we use this? How do we use this? What I want you to do is you figure out what variable you want, right? So in this case, if you look at our equation, D, that's the variable we want, it's by itself. So I want in your triangle, I want you to cover up the D. If you cover up the D, what's left? You got an M on top of a V. Just looking at a triangle, you see you have an M on top of a V. Well, that's the other side of our equation when you look at our equation here. D equals M over V. You can do the same thing for the other variables. If you want to know what the equation is for mass, you say mass equals what? I want you to cover up that little m for mass. And what do you have left? You have a D next to a V, so it's D times V. So here we'd say mass equals density times volume. And finally, if you were looking for volume, I want you to cover up the volume. And what do you see? You have an M above a D, mass divided by density. So our formula for volume is volume equals mass divided by density. So hopefully this triangle trick helps you. Now, again, our density for water, remember, 1 gram per milliliter. I want you to remember this. 1 gram per milliliter. Now, what's the little m stand for? We told ourselves little m stands for mass. What do we measure mass in? Well, usually we'll measure it in grams, right? Usually we'll measure it in grams. Now, V stands for volume. If we're talking about a liquid, we measure the volume of liquids in milliliters. Remember our graduated cylinders, I told you they measured volume in milliliters. But if we're measuring the volume of a solid, right, we measure that in cubic centimeters. Think about that for just a moment. If you had a cube and you wanted to find the volume of it, you'd multiply the length times the width times the height. Those measurements all have centimeters in them, right? 5 centimeters long, 10 centimeters high, 2 centimeters deep. Well, if you multiply those together, you're going to multiply all your numbers together, but you have to multiply your units together too. And centimeters times centimeters times centimeters gives you centimeters cubed. So the volume for liquid we're going to measure in milliliters, but the volume for solid we'll measure in cubic centimeters. Tricky one. I want you to remember that one as well. So then we do our density calculation, right? Liquid density, remember we talked about density is mass over volume. So if we're measuring the density of a liquid, we're going to say grams, but we're going to divide that by milliliters. the unit for density volume of a liquid is milliliters. So when we calculate the density of that liquid, we're going to use grams per milliliters. Solids, though, hopefully this makes sense. We're going to measure the mass still in grams, but we measure the volume here in cubic centimeters. So we measure the density of a solid. The units are grams per cubic centimeter. Right. Then we'll do a few practice problems here. I want you to focus on sig figs too. Remember, we learned sig figs last week. So let's start with this. A block of aluminum occupies a volume of 15 cubic centimeters. So it's a block of a solid, right? So we're going to measure that volume in cubic centimeters. And it has a mass of 40.5 grams. What is its density? Well, hopefully, remember our little equation, D equals M over V. So let's just plug in our variables, 40.5 grams divided by 15.0 cubic centimeters. Our density is 2.7 grams per cubic centimeter. Okay. Don't forget to put your units at your answer. Now we have 3 sig figs here. Right? Your calculator told you 2.7, but we were told we had 40.5 grams of our material. There's your 3 sig figs. We had 15.0 cubic centimeters. Again, 3 sig figs. So our answer better have 3 sig figs. Our calculator only gave us 2. How do we make the third? We just put a 0 at the end. Let's do another one. You find a piece of gold that has a mass of 528.4 grams. And this time we're going to ask you for the volume. Right? So give you the density is 19.3 grams per centimeter cubed. So we have to rearrange our equation. Right? We can't use our base equation, density equals mass over volume, because we're not looking for density here. We're looking for volume. Well, hopefully, if you remember using your little triangle, you're going to see your cover up. You have the mass in the top and the D and the V in the bottom. Cover up the V because that's what we're looking for. What's left? Mass over density, M over D. Well, let's plug in our numbers. 528.4 over 19.3. And your little calculator is going to tell you 27.38. But we're only allowed 3 sig figs. Right, the 19.3 grams per cubic centimeter, that measurement only had 3 sig figs. So our answer is only allowed to have 3 sig figs. So if you look at that to the 27.3, there's our sig fig, 3 sig figs. The 0.8 after that, or the 8 after that tells you to round up. So we're going to come up with an answer of 27.4. That's our numbers. What are our units? We have grams in the top. We have grams over cubic centimeters in the bottom. Hope you'll recognize the grams and the grams cancel. Grams on the top and the grams on the bottom cancel. What are we left with? Milliliters, cubic centimeters, but that's in the bottom of the bottom. When it's in the bottom of the bottom, that's the same. You have to flip it out to the top, and you have set cubic centimeters by themselves. Our answer will be 27.4 cubic centimeters. Let's do another one. Find the mass of 250 milliliters of benzene. Density is 0.8765 grams per milliliter. So our first problem, what did we see? We were finding the density. The second problem, we were finding the volume. This third problem, now we're asked to find the mass. So again, I want you to remember your base equation, D equals M over V. Use your little triangle. How do we arrange our triangle? We're going to cover up that M in the top. What are we left with? We have a density times volume. That's going to be our equation. Mass equals density times volume. So let's plug in our numbers. 0.8765 grams per milliliter times 250 milliliters. I'll put those together in your calculator. It's going to tell you 219.125. But how many sig figs are we allowed? 250.0. That decimal makes those zeros count. That makes those trailing zeros count. So we have 4 sig figs there. 0.8765. Well, the zero in front is leading, which never counts. So we have 4 sig figs there. Our calculator gave us 6. So let's look at our first 4, 219.1. What's the next number? It's a 2. That tells you we round down or just leave it alone. So our answer is going to be 219.1. Now, what are our units? Our density was grams per milliliter. We multiplied that by density is grams per milliliter. We multiply that by our volume of 250 milliliters. So we have milliliters in the bottom, we have milliliters in the top. They're going to cancel. What's left? Just grams. So our units are going to be grams. Here's some answers for the rest of our sig fig worksheet. I want you to try that worksheet here. It's posted in the folder below. And then check your answers against this. All right, guys. Talk to you later. Bye-bye.